No, RCB, again R, C and B. So it is applicable to all the three classes, R class, C class and B class, baffle and support plates. So what is given in RCB 4.1 for the transverse baffles? Transverse baffles and longitudinal baffles are the two different types of the baffles. Transverse baffles are the one which are perpendicular to the flow, or we can say uh, which are having a transverse cut as compared to the flow direction. The segmental baffle are most commonly used type of the baffles. However, other type of baffles are also acceptable. So when we are saying segmental baffles, so these segmental baffles are single segmented, double segmented, triple segmented. So we are going to see that how these segmented baffles are being classified. Baffle cut is defined as every segmented baffle is having its cut. So that cuts is defined in two ways in Tema. One is in percentage of shell inside diameter. So let's have a look at if it is been represented in percentage shell diameter, then how it needs to be calculated or how the cut needs to be provided. Because in process data sheet or from the STRI report, we will come to know about how much is the percentage cut on diameter or on net area that has been specified. So if it is specified in terms of percentage of shell diameter, let's take one example. So shell ID is equal to 1000 mm. And if let's say percentage cut is defined as 25%, if it is being defined as 25%. So if in 1000 mm 25% cut is there, so let's say this represents the baffle cut. This remains 750 mm, which will be remain in place, and this 25%, which is nothing but 250 mm, will be removed. This will be removed. So this is how the 25% cut will be defined, that in whenever there is a 1000 mm diameter, so 250 mm will be the cut and 750 mm will be the remaining, which will remain in place. So one cut will be like this, another alternative baffle will be having this side full and this side there will be a cut. So there will be alternative cut so that the fluid can pass through, pass across it like a serpentine movement. Now, in percentage of total net free area, there are two ways it has been defined. First is in percentage of shell ID, and another thing is in percentage of the total net free area. So, how to define this total net free area? A net free area. So, let's have another example. Let's say this is again a cross section of a shell with number of tubes. You can see that this brown color or maroon color area is there, right? That is called as a total net free area. So calculating the cross sectional area of the shell and subtracting the cross sectional area of all the tubes, whatever is remaining, this space is representing the net free area. So shell ID is, let's say, 1000 mm, percentage cut is 25%, again the same, but now it is been defined in terms of total net free area and not in terms of shell ID. So let's say if it is been specified as total net free area 25%, then how to calculate is shell cross section area we have to first calculate minus cross sectional area of all tubes, that is your total net free area, and out of which 25% is removed. So that 25% we need to calculate, and then we have to draw a line which will reduce or deduct the 25% net free area. So it's a trial and error method by which you can get that total area, how much it will be deducted from this, or the line or the distance by which you should supposed to have this baffle cut line. So once it is been defined, then the same will be followed across the baffles. So this is one in terms of shell ID, another in terms of total net free area. Most of the time, 95% of the time, you can see that it is very simple to get in terms of shell ID. So that's the reason why it is always been represented in terms of shell ID, the percentage cut. It is rarely has been specified in total net free area. So what is the cross sectional area of the total shell? Pi by 4 into d square. D is nothing but the shell ID, minus pi by 4 into OD square. D is nothing but the OD of the tube. Pi by 4 OD square into number of tubes. So this is how we are going to calculate the area of the tubes, and whatever subtraction is coming, that is this maroon color area, which is total net free area, and from which 25% you have to calculate, you have to multiply it by 0.25. So whatever is remaining from that, you have to calculate the width or the dimension of that cut, and then you have to define that cut over here. Now RCB 4.1, types of transverse baffles. As we are discussing about transverse baffles, how many type of transverse baffles are there? Single segmented baffles, multi-segmented baffles. These multi-segmented baffles further have the division as double segmented baffle and triple segmented baffles. So single segmental, double segmental, and triple segmental baffles. So let's start with the first, which is single segmental baffles. So what do you mean by single segmental baffle? Means only one segment has been removed. Most commonly used type is single segmental type, not recommended for the vibration prone condition. These single segmental baffles are not commonly used wherever there is a high vibration possibility. Why so? Because it is having a percentage cut in terms of there is only one cut, and let's say there are tubes over here also, right? And those will be supported only by the next baffle. So let's have a look at, I will show you in that diagram where we have shown the baffle arrangement. So let's say we are going to discuss about single segmented baffles. So single segmental baffles have the cut only one side cut will be there, right? Now imagine these tubes. These tubes are supported till this point. So the unsupported span would be like this. But if you see or look at this tube, so this is not being supported over here. It is directly passing through the gap. That gap is called as a baffle window. That is called as a baffle window or tube bundle window, from which it is passing, and it will be supported only on the second baffle. So the unsupported span would be much more for the tubes which are nearer to the nozzle. So if the flow is coming over here and it is passing through here, so what will happen? The first tubes onto which the impact will happen, so these tubes are not being supported for the shorter distance. They are supported by the second baffle directly. So because of this larger unsupported span, the vibrations would be higher. So to avoid that, what we are doing, double segmental or triple segmented baffles we are selecting, where the support will be provided from the shell diameter. Let's say from top and bottom, and in middle there is a gap for vertical heat exchanger. We can have that kind of arrangement. So that what will happen? So because of that, the unsupported span would be minimum, and because of that the vibration possibility will be little, or even if it is there, then its severity will be controlled. So single segmented baffle most commonly used but not recommended for the vibration prone conditions. So here in single segmented baffles, there are three types of cut. One is horizontal cut. You can see over here, this cut is horizontal, and the flow direction would be like this. The flow direction would be like this. So the flow will go like this, come down again from bottom, it will go, again it will come up and come down. So there will be a zigzag kind of a flow like this if there is a horizontal cut. Then the second one is a vertical cut. Here you can see the cut has been provided in vertical direction. Now how the flow will come? The flow will come like this, perpendicular to the direction of the baffle cut. Always do remember that the direction of the flow would be perpendicular to the baffle cut edge. So here the baffle cut edge is this, and perpendicular to that means in this direction the flow will happen. So let's say the flow is happen now in zigzag condition across this baffle. So this is vertical cut. And another cut is called as a rotated cut, which is 45-degree cut also, or it would be as per requirement any angle at which it will be inclined based upon the process requirement. So this is rotated cut, horizontal cut, vertical cut, and the rotated cut. Actually the flow will come from this direction, but since been it is been rotated in such a way that it has to pass through direction perpendicular to this. So how it is going to happen? So let's have a look at. So this is the way the flow is going to move across the baffle. So now let's have a look at again single segmented baffle, which is horizontal cut, and let's see how it is going to direct the flow inside the heat exchanger. So let's say these are the single segmented baffles. Again here the tubes are not being shown for better representation of the flow so that the flow can be easily viewed. So let's say these are single segmented baffles. So you can see over here, if the fluid is coming, then first baffle cut has to be provided on this side so that the flow can transfer like this, right? So the direction of the flow would be like this, zigzag or serpentine shape. So the fluid is coming from top and it is going to the bottom, and the movement is like this. It will follow this path across the tube bundle and the baffles are going to direct it. So this is how the flow direction would be perpendicular to the baffle cut edge. So how this horizontal cut will look like? So you can see over here, this is again a heat exchanger. Here we have a made transfer on the shell side so that you can be having a better understanding of this type of percentage cut. So you can see over here, this is horizontal cut, horizontal cut. Alternatively, you can see here that horizontal cut is been given, and from bottom also you can see the cut has been given in horizontal manner. So one is having the cut at the top, another is having bottom, and it will be vice versa, top bottom, top bottom, top bottom. Similarly it will be having in case of horizontal heat exchanger, it will come, it will feel come up down, come up down, come up down, like this it will happen. So you can see it from here also. If let's say the inlet is from this side the inlet is there, then it will fill up, then go down, fill up, go down, fill up, go down. So let's say this side also, if the inlet is from this side, it will fill this, then it will travel at the top perpendicular to this edge. This is a baffle cut edge to which it is perpendicular. Then it will fall down. Again it will come up. Again fall down. Again come up. Again fall down. So this is the way it will transfer. This is the way it will transfer to the tube bundle, and it will create more and more turbulence and increases the heat transfer coefficient. This is horizontal cut. This is vertical cut. So if it is vertical cut, the flow direction has to perpendicular to this baffle cut edge. So again now you can see over here it is having a vertical cut. Vertical cut. Horizontal one. So here it will pass like this. Let's say now this again is inlet, it will fill this portion, goes like this, then come like this, goes comes, and it will be in serpentine motion. It will be having a flow to happen across the bundle. So this is a vertical cut type of single segmental baffles. You can see this cut is not now horizontal, this is vertical cut. Few of the tubes will pass through this tube window, few of the tubes will pass through this baffle window rather, we can see, and those will be supported by alternative baffles only. So the tubes which are coming after this, those will be supported by this baffle. The tubes will be which will be going after this baffle cut, that will be supported by alternative baffles. So first, third, fifth, seventh, these are the numbers of the baffles which are supporting some tubes, and 2, 4, 6, 8, these are the numbers by which the tubes will be supported by even number of baffles. And there are some baffles which are supporting the tubes which are connected to the tube sheet. So from tube sheet, some tubes are supported at the first baffle, and those who are passing through the window are supported directly by the second baffle. So few of the tubes are coming from here, and those are supported only by the second one. And here also the same. Few of the tubes which are connected to the tube sheet are supported only by this. So there the unsupported span would be more. Now rotated cut. Now the flow direction would be like this. So you can see over here, this is the cut which is represented like this, and the flow will come and then it will go like this, which will be perpendicular to the direction of the baffle cut edge, perpendicular to the direction of the baffle cut edge. So it would look like this. So the flow without shell, if you just represent the tube bundle, so it will look like this. So this is the way the flow is going to happen perpendicular to the baffle cut edge. So depends upon your process requirement and the way it is been mentioned in the process data sheet or in your thermal calculation sheet. We have to follow the percentage cut, whether it is single segmented, horizontal, vertical, or rotated.